illustrious career and continues to do so in all aspects of stochastic optimization and control, covering the entire spectrum of theory as well as applications. So he's currently an emeritus fellow at IIT Bombay, and previously he's been with TIFR, IISc, and many other institutions during his studies as well, including IIT Bombay, Case Western, and Berkeley. So without further ado, it's a pleasure to welcome you, Professor Borkar. Over to you.
Thank you, Aditya, and also want to thank Shalab and Ambedkar for their invitation. So can you see the slide properly? I have some garbage sitting at the bottom.
Yes, we can see the slide ending with DR.
Okay, good. Okay, so I'll start with a line I borrowed from Monty Python, and now for something completely different. The reason being that my talk is substantially off the main theme of this workshop. In particular, there's nothing deep anywhere. Okay, so don't believe the rumors that I'm already going off the deep end. They're not true. So there's also joint work with Konstantin Avrachenkov of India, Sofia Antipolis, my colleague Sharayu Moharir, and my former student Suhail Mohammad Shah, who is no postdoc at Hong Kong University of Science and Technology. I'll begin with a list of things I'm not going to do. So basically, this work combines several ideas from all over the place, but I want to highlight one idea, that of annealed landscape by analogy with simulated annealing, which might have other uses. And there's some routine stuff about modeling and several parts of the techniques used are kind of standard for people who are either in stochastic approximation or related areas. So those also, by and large, I should skip those. And also there is there's some part which is excessively technical, and I'll just give some kind of verbal intuition. Okay, and also I'm not including numerical experiments. Okay, so the model is as follows. So you have a sequence of agents who arrive one at a time, and they make a choice from finitely many options and get a noisy reward each time. The choice probabilities are proportional to some function f of the total reward accrued by people who chose the same item in the past. So when I join the gang join the people who are trying to buy whatever, I see how many people bought various things, and then I have a function which maps that into some choice probabilities for me. Okay, and this is kind of not an entirely new kind of model. Such models have been used in economics in particular, where they call it increasing returns, also herd behavior, and engineers would probably call it positive reinforcement, and so on. Okay. And the function f I have chosen to be positively homogeneous, because what we do is to have the choice probability proportional to f, so they should not depend on the scale or what unit you choose. Whether you pay in dollars or rupees shouldn't matter. The convergence factor should cancel out. So we are taking it to be positively one homogeneous. I should have said one homogeneous. So that is independent after normalization of the scale factor. And they also depend on a parameter alpha, and which is chosen so that they concentrate more and more on the more rewarding options as alpha increases. And if you let alpha tend to infinity, it will pick the max reward. So it's if you the alpha tending to infinity would correspond to a greedy policy. So the idea here is to let alpha go to infinity slowly, and we call alpha the inverse temperature by analogy with simulated annealing again. So okay, I'll talk about the difference with simulated annealing later. So there are two results. First, we just fix alpha, and we get a probability one, almost sure convergence to one of the many possible equilibria, which can depend on the sample path. So this convergence to some equilibrium. And this is what sometimes is called the curse of non-linearity. And similar to tapping phenomenon increasing return economics, which was studied notably by Brian Arthur and Paul David. And there are a lot of interesting examples. I mean, it's a non-trivial issue. Typically, what happens is that this kind of positive reinforcement can get you trapped into a non-optimal equilibrium. They have some serious examples of it. For example, adoption of some less than optimal technology. For example, US adopted for the nuclear reactors cooling technology which was pushed by US Navy, and which is not the best. And so the latecomers like us have actually a better technology, but because it got set in and people became the kind of, see, there are things like networking effects or whatever. And once you are stuck with something, you are stuck with it. Another interesting example is the typewriter, the arrangement of keys on typewriters, what's called QWERTY, because you see the top row is QWERTY. That was designed for mechanical typewriters because you didn't want two keys which are likely to be pressed one after the other to be too close to each other so that they don't interfere or jam. But now in the electronic era, it doesn't make sense to use that. But there was a proposal which was ergonomically better called Borkar, but it didn't catch on because people are too used to QWERTY. There are also some exotic examples in some of the popular articles of Arthur. Here's some 12th century church in Italy where the clock goes anti-clockwise. So apparently they could go either way, but eventually people got used to clockwise clocks and so on. And similarly, for example, the driving habits, like, drive on left or right. Apparently it was dictated by the fact that earlier people rode horse carts, and if you drove on the left and use the whip to whip the horse, you could accidentally whip the driver on the other side of the road. So except in Britain, where probably it didn't matter because the owners of the horse cart probably simply sat inside and didn't care what went on outside. They drove on left, and so do we. But from everywhere else, they drive on right. Anyway, so these are just curiosity items of how this kind of nonlinear recursions end up in equilibria, which are not necessarily the best. So what we do here is, as I said, you increase the inverse temperature alpha slowly, and that can be shown to lead to the correct equilibrium in the limit. And one can give some kind of anthropomorphic interpretation that as time increases, the agents gain more and more confidence in what they see, because there's a lot more history to learn from. And therefore, they can kind of concentrate their probability more on the winners. Okay, so this is what we call annealed landscape, and this distinct from simulated annealing, classical simulated annealing, in the sense that it's the objective function which is being manipulated and not the noise. Okay, in simulated annealing, you add noise and slowly decrease it. So the noise facilitates uphill moves, so it facilitates exploration, but you don't want it to stay around forever, so you slowly tune it down at a certain technically precisely specified rate. Here, what we are doing is actually tweaking the objective function itself. And one way of thinking about it is that it operates on the stochastic approximation timescale and not the simulated annealing timescale. So it's not that slow. Of course, stochastic approximation is slow in general, but it's not as slow as simulated annealing, which is extremely slow, and nobody uses it in its vanilla form. Maybe. Okay, so there are some examples here to motivate the customers on e-commerce portal buying items based on average rating times the number of reviews, and then moving on to the next purchase based on recommendations. Okay, this last part actually comes later. I have not specified yet what I mean by graphical constraint. So the part that you actually decide based on recommendations and what ratings you see combines both of this. The fact that you look at the ratings times number of reviews is the part I have already described. But the fact that your search of the next purchase is restricted to recommendations is what I call graphical constraint. I'll come to that later. Similarly, autonomous agents scanning an area while being constrained to only to adjoining positions. So this constraint on movement is also a graphical constraint. Okay. So this actually no work that we know of, which is very close to what we do, but these are relatively the closest. In fact, the first one by Vivek, Shah, Vivek Blanchett, and Ramesh Johari, this is what prompted this work. So they have this something in bandit framework. They introduced something interesting called balanced exploration. So they explore for a certain length of time where they ensure that every arm is sampled at least so many times, some minimal guarantee. And thereafter, they use whatever they have learned and give kind of concentration bounds. Then this Cohen, Helu, Matikopoulos, they go for full-fledged game theoretic learning for bandits with potential games. And that's the closest in terms of techniques. There are some similarities in terms of that kind of thing we use. The ours is more general.
Professor Borkar, there is a question by Sanjay Shakotai. Sanjay, if you can unmute and ask you. Sanjay, can you speak?
Can you hear me?
Yes.
Yeah. So I was wondering, you talked about the simulated annealing timescale and the stochastic approximation timescale.
Yeah.
By simulated annealing, do you just mean it's a pure diffusion, so it's extremely slow, it's just random, it's random walk, whereas with stochastic approximation, you have 1/√n. Is that what you mean?
Yeah. So if you look at, for example, if you look at the simulated annealing in continuous Euclidean spaces by this Gelfand-Mitter, okay, you see that they have the stochastic approximation step size for the gradient term, but you have to see that suppose you use gradient, the stochastic approximation step size 1/n, okay, then that means the algorithm moves on a log n scale because sum of 1/n goes as log n. And what they do, if you add noise on the same time scale, it's going to 0 too fast for simulated annealing. It doesn't allow you to escape the local optima. So what they do is they have another step size for extra noise they add, which is some constants divided by square root 2n log n, which basically, if you go to the continuous limit, it becomes cy log t, which is what is required for the simulated annealing. So, and that's very slow, that decrease of noise. So another way to think of this is the Lagevin algorithm is dxt is minus grad v xt dt plus epsilon t dwt, where epsilon t is as c by log t, okay. So let's just call it epsilon t. Suppose I move it, change it to dxt equal to minus 1/epsilon t grad v xt times square root epsilon t. Original algorithm, if I put, I forgot a square root. The original algorithm is dxt equal to minus grad v xt dt plus square root epsilon t dwt. And I change it to dxt equal to minus 1/epsilon t grad v xt plus dwt. I am just changing the time scale. So moving 1/epsilon to the objective function. And that's roughly what we are doing. So it's like a highly accelerated simulator.
Thank you.
Okay, so the main results are, okay. So as I said, you consider a stream of agents running one at a time and choosing one of m greater than one distinct objects probabilistically. So I use psi n to be, actually this should have been one, there's a typo. It's an indicator from, sorry, it's not a typo, it's correct. Psi n is I, if the nth agent picks object I, and SIN is the sum of indicators of psi k equal to I of prime n. So it's the number of agents who pick I till time n. And SIN is SIN by n, that's the fraction of agents. So that's the total n agents who have come so far. And so SIN by n is the fraction of agents who pick I till time n. Then it's a routine calculation with people who have seen Earn models. Actually, what Brian Arthur, etc., used is nonlinear Earn models. You can just write this recursion for the fraction of agents. Okay, it's xin n plus 1 is xin plus 1 by n plus 1 times this. Okay. So it starts looking like stochastic. It is stochastic approximation, taking values in the probability simplex. So this is a probability vector by construction. It's a fraction which adds up to 1. I've taken uniform initial condition that's not crucial. It will get swamped out by the iterates anyway, sympathetically. And so it's a kind of stochastic approximation or Earn model. And the graphical constraint is that I assume I have a graph, direct reducible graph, with a vertex set V and script V and S set script E, and M is the size of the vertex set. So M is the number of items we are considering, and I assign each node to each one item. Okay, and then there's some neighborhood structure. So script Ni is the neighbors of I. So nodes J such that there's an edge I from I to J. And this important assumption that this relationship is symmetric. Although it's a directed graph, I assume that if I can pick J after I can also pick I after J. So there's kind of in the recommender system, there's similar items. So if you bought I and somebody recommended J, then if you bought J, the same machine would recommend you I as well. And let Fn denote all the information every time in the sigma feature to this. Then the way I choose the next item is 1 minus epsilon n times. So epsilon is a small parameter which I decrease to 0. 1 minus epsilon n times some probability function which I'll specify soon, plus epsilon n times just a uniformly random. So this is some kind of exploration. I shall say more about this. So chi is just uniform distribution on the set of neighbors, which I pick with some small probability, but with bulk of the probability, I follow this rule which the algorithm gives, some p sub alpha sub. So this is the probability of going from psi to j when my current fraction is xn. Okay, so it's not a fixed probability. It depends on xn, and it's described on the next slide. And I want to emphasize, I probably say that somewhere. Just in case I don't, let me emphasize that this looks like I'm contradicting myself. I'm adding a small noise like simulated annealing, but it's a more tame version of it. This noise allows me to, so simulated annealing allows you to get out of all critical points other than global minimum. So it allows you to get out of saddle points, local maxima, points of inflection, and local minima which are not optimum. What here my aim is limited. I just wanted to get out of things which are not local minima. That's easier. What will get me out of local minima? In fact, sorry, here it's a maxima. So what will help me get out of local maxima is the fact that I'm tweaking, allowing alpha go to infinity. So that's where the difference comes. So the probability is you move of course to a neighbor. So this is a symmetric relation, as I said, proportional to this function f alpha, which I choose to be this. Okay, so it's it's positively homogeneous. It doesn't have to be one homogeneous. It's alpha homogeneous. Alpha equal to 1 is a special case, which I won't discuss today. And if you so whatever, if I multiply this by some constant, it will cancel out because the same constant stays in numerator and denominator. The real model actually, see if you knew mu, which is the mu corresponds to the reward for the mu j, the reward for the jth item. If you knew mu j, there's nothing left to do. So of course you are not going to do this. So there's some estimate of mu hat n you work with, and that also improves with time. But I'm going to assume take this. So as I said, I'm skipping the part of the arguments which are more routine. So what we'll do is this is the actual model. So you don't know the mutes, and there's some estimation scheme involved to estimate mu, and that's what you plug it in. But asymptotically, anyway, I'm only looking at the asymptotic analysis. I'm allowed to replace this mu hat I n by mu hat I. So that's what I'll do for sake of analysis. Okay, so this part is relatively easy. The passage from this to that is, I won't say easy, but it's standard. So nothing surprising there. Okay, so let me go to the next slide. And if I fix x and pi alpha x, which is given by this, and that's just a fact of the fact that it solves the local balance equation for the corresponding constant probability. So once I fix x, it's just a fixed constant probability, and then this normalization works. So the plan is to treat Xn as a stochastic approximation algorithm and then use the ODE approach due to Markov. It was actually originated in Russia, Markov, and for Markov noise and derivative scheme Markov for the martingale noise, if I remember. And later on, Jung kind of expanded it and popularized it in the Western world. And somehow these people seem to get forgotten at times. So I always make it a point to mention them. And what one does is to treat the stochastic approximation as a noisy discretization of a differential equation, and then argue that it will track the same, it will asymptotically have the same behavior as the ODE. So because Sean Mayen already went through this, I'll go somewhat, I have a minor tutorial here, which is a little different from what Sean did, but so I'll go through it anyway, but slightly faster. So this is a kind of general stochastic approximation algorithm. I have three kinds of errors. This Yn is what I will call Markov noise. Iota n is some small asymptotically vanishing error, which is the least offensive of the object. And Mn plus 1 is the martingale difference noise. So, okay, the idea is that what you observe is your measurement is this entire thing. You don't see them individually, so you cannot handle them separately. You're stuck with the sum. So, and Fn is the sigma field generated by the history. The step size scheme, as per Robbins-Monroe, is sum of n is infinite, sum of n square is finite. I'll explain why that matters. Martingale difference noise is just a kind of a sequence of uncorrelated. So Mn plus 1 is uncorrelated with the past. That's what this says. So that's by technically speaking, this is a martingale difference noise, but you can think of it as uncorrelated noise. Iota n is some bounded random variable going to 0, surely. Yn is the most complicated thing. It's a Markov noise, and it takes. I assume it takes values in a finite space because that's enough for us. But one can go more general, and it satisfies. It's like a modulated Markov chain. The probability that Yn plus 1 takes value j given Fn depends only on the previous state according to a transition probability, but a transition probability is modulated by your iterate xn at time n. So if I assume that if you fix x, then it's a irreducible Markov chain. Will have a unique stationary system pi sub x. Okay. So just note that Yn is a kind of modulated Markov chain operating on the natural time scale n equal to 1, 2, 3, 4, ... But Xn is moving on the algorithmic time scale, which is A0, A0 plus A1, A0 plus A1 plus A2, etc., which Sean also had introduced it. He called it tau n. It was the sum of AI equal to 1, 0 to n. So it's moving slowly. So what you expect is that you expect some averaging effect to take place. And that's what happens. And you get a limiting differential equation is z dot t equal to sum over j of pi sub zt, j h of zt comma j. So the iota n is going to 0 anyway, so it's asymptotically negligible. The martingale noise is 0 mean, martingale difference noise is 0 mean by definition, because the conditional expectation was 0, so its mean is also 0. One can show using martingale arguments that it averages out to 0, so it drops out. But the Markov noise doesn't drop out. What it leads to is averaging with respect to the corresponding stationary distribution. So if this differential equation, you look at this differential equation and look at its asymptotics. So the condition n going to 0, which implied by the square summability, implies that the discretization errors are asymptotically negligible. Square summability ensures thus this martingale, since m plus 1 is a martingale difference sequence, this sum is a partial sum is a martingale, and martingale convergence theorem tells you that this is convergent, and therefore the convergent of a summable quantity is tail of implies that its tail, the sum from n onwards goes to 0, and noise from time n onwards is the tail of this thing, and therefore it's asymptotically negligible with probability 1. So that's why the martingale noise drops out. n going to 0 also ensures that the drift gets averaged with respect to the modulated stationary distribution. This also I mentioned. Some n equal to infinity, because I am treating n as a time step, ensures that you are actually approximating the ODE on the entire positive time axis. Okay, and therefore you track the asymptotic behavior. If this was less than infinity, you would be simulating the ODE on a finite time interval, and that won't tell you much. So this, as I said, some am from 0 to n minus 1 and so on. What you do is write this, define this interpolated trajectory z bar. Z bar Tn is just Zn, and then you interpolate just take linear interpolations. And then basically you take a moving window. So if you just consider from 0 to some time capital T, you are in trouble because the errors keep accumulating. The correct thing to do is to move on, compare the interpolated iterates and the differential equation on a moving window, T to T plus capital T, with their initial conditions matched, and then you use the good old Donald inequality to show that the error between them goes to 0 asymptotically. So that's sort of a crash course on the ODE method. It's worth learning because once you have understood it, then you can forget where it came from, and you can basically plug it in blindly. In fact, it goes both ways. Given the algorithm, you can write down the ODE by inspection and then you look at the ODE. Conversely, you have to think of an algorithm, think of a convergent ODE and discretize it with noise. The general limit theorem is due to Michel Benheim, which I'll just mention it. I mean, not every ODE has to converge to an equilibrium, but it says that it will converge to what's known as an internally chain transitive invariant set of the differential equation. It's a notion from dynamical systems due to a mathematician called Conley, and it's anyway, I won't get into this. It helps in a non-convergent scenario, for example, game theoretic scenarios, where your environment is depends on what you do and what your friends do. So convergence is not easy. So now the one special item, the 2 times stochastic approximation, my iterates are x comma y, but I've split them. I'm using different step sizes on n and for x and y. Both satisfy the Robinson-Monroe conditions, the sum to infinity and square summable, but bn by n goes to 0. So what this means that this decreases faster to 0. So this is moving on a slower time scale. So you can, when you look, you can analyze x pretending y to be constant because it's on the time scale defined by n. This is so slow because bn by n is going to 0. They can pretend y is constant and analyze this ODE x dot t equal to hxt comma y. And then you suppose xt, you can show that xn converges to lambda y, the ODE. Then what happens is that xn will track lambda y. Because of this, g of xn comma yn, this was g of xn comma yn here, that becomes approximately g of lambda yn comma yn, and yn will track this ODE, where the x doesn't show. So suppose this converges to y star, then x and y will converge to lambda y star almost surely. And this kind of emulates nested iterations. So if you have nested do loops, so the outer iteration runs a subroutine. So the slow variable y is the outer iteration. Suppose at during each iterate of y you want to run a subroutine for x till convergence. So what one typically does is to run it till near convergence, take that value, and then go for the next iterate of y. What this allows you to do is to concurrently update both, just using different step sizes, and you get the same effect. So this is kind of a good way of emulating nested iterations, one subroutine inside the outer iteration, and just do away with the inner iteration by just iterating both simultaneous, but with different steps. So let's return to the original thing. I hope that was not too fast, but counting on my predecessors in this workshop, well, enough of this already. That is hopefully not too much. I'm slightly worried about. Anyway, so let's return to our problem. So what do we define phi alpha I? Is this, and this turns out to be the differential equation, limiting differential equation for empirical measures of a vertex reinforced random walk. Okay, so this is a random walk where the probability of moving to the next vertex depends on how often you have visited it already. So typically you use positive reinforcement. So that's what we also do. So what I call the go back to where you once belonged philosophy. So it will tend to visit nodes which you already visited often with higher probability. So if you if this was not there, if it was a vanilla random walk or a vanilla Markov chain, this would actually reduce to the usual forward equation for forward Kolmogorov equation for the distribution phi t of a say, continuous time Markov chain. Okay, these are nonlinear analog of that because the transition probability depends on the current empirical measure. So I mean, those who have seen kind of the current rays, the mean field dynamics, etc., are used to nonlinear Kolmogorov equations. This is one other nonlinear Kolmogorov equation. So this was studied extensively by it was introduced by Robin Pimentel, and it was recognized as a stochastic approximation by Michel Benaim. No surprise, I mean, the stochastic approximation man, and he analyzed it using ODE limits. So the usual thing is some kind of a linear reinforcement function, which he analyzed extensively, and then he gave some general results for nonlinear case as well. And later on, he and his collaborators have put some exotic results about limiting behavior. For example, we can show that it, and others also like Volkov. So a lot of probabilists proved interesting results which interest probabilists, but for us, actually, not all of that are of interest. That is of interest. But what I want to say is that we also consider a nonlinear scheme, but it's a spatial nonlinear scheme. So it's somewhere between linear and general nonlinear. So because it's a very spatial, has extra structure, we can do more. So once sorry, where was I? Yeah. So this equation, suppose I multiply by the denominator on both sides, I can convert it to this equation, which is a well-known equation in evolutionary biology called replicator dynamics. So here I look at ZIT, which ZI dot t, ZIT times this. So it sits in the probability simplex. So ZIT is a probability vector, and the interpretation is that ZIT is the fraction of species I at time t for the biologists. This is the reward of species I at time t if the current population profile is zt. So what it says is that the reward you get is more than the average reward of the population. So this is the reward of species j. You multiply it by fraction of species j and sum it. So it's the average population reward. So if you're doing better than population, your fraction will increase and not otherwise. So because of that, as long as ZIT is strictly positive, so this is just a time-scaled version of this basically, and it has the same trajectory. And this helps us. We use this fact because in general, replicator dynamics need not converge. It can have even chaotic behavior, etc. But for a special class of payoff functions, which are called potential games, namely this, if this object phi sub alpha sub I of z is a gradient of something. So here I have called minus phi alpha. Okay, so usually people look at minimization, hence the minus. It turns out to be the basically gradient of this thing. So if you were doing minimization, you would put a minus there and call this a Lyapunov function. But here actually this Lyapunov this function increases. So one can prove, I mean, this is not a just known fact that this potential function will increase along this trajectory, and therefore this ODE will converge to the local maxima, or they're in the interior or the set of local maxima, let's say. So I'm assuming I'm going to impose some interesting condition which saves even more work. That the equilibrium points of the ODE assume that they are isolated and hyperbolic. And also their stable and unstable manifolds intersect transversally if they do. So by hyperbolic, what I mean is that if you linearize the dynamics around the equilibrium point, then it is known that basically the stability properties are reflected in the linearized system. So if the eigenvalues of the Jacobian at that equilibrium, eigenvalues of the right hand side of Jacobian of the right hand side of that equilibrium are not on the imaginary axis, I call it hyperbolic. So they're either on the left hand side or the right hand side of the imaginary axis. Okay, this is what's known as a structurally stable situation, because if you perturb a matrix a little bit, the eigenvalues change a little bit. So in this case, if the eigenvalue is strictly on the left, if you perturb it, it will remain on the left. If it's strictly on the right, you perturb it, it will remain on the right. So qualitative properties don't change. But if it's on the imaginary axis, it could go either left or right, and you are in trouble. Though things don't become impossible, but I will stick to this simple situation where structure is stable. In this case, it's known that the local linear linearite dynamics reflects the overall dynamics. That's called Heartburn theorem. This assumption is actually in dynamical sense called it's a special case of what's called a Morse-Smith system. They also allow for limit cycles. But the extra thing you need is that this is also so corresponding to stable eigenvalues of the equilibrium, the linearized, there will be stable manifolds, and corresponding to unstable eigenvalues, there will be unstable manifolds, and they have to intersect transversally in the sense that they should be tangential to each other. This is also a structurally stable thing. Okay, so if two things kind of are not tangential, if you put up them, they can either separate out or cross each other. You don't know what happens. But if they are not tangential, think of two surfaces which are not tangential, they cross each other. So if you put up them, they still a little bit, they still cross each other. This is also a structural stability requirement. So, okay, I don't know if I have any details on this. Yeah, probably not. So again, I'll verbally describe what happens. So if there's even one unstable direction, okay, so what happens that if you are on stable manifold, anyway, I'll return to this later. So what happens is that if there's even one unstable direction, almost all trajectories will diverge. Okay? They won't converge to that. That's because of the noise. So if there's time towards the end, I'll talk about that. So what happens here is that one can show that xn will convert to a possibly random local maximum with probability 1. So what my addition of that epsilon n noise is achieved is that it won't convert to any other critical point, in the sense that it won't convert to a local minimum or a saddle point or a point of inflection or whatever. Of course, this being a kind of ODE in a probability simplex, so I have to also allow a thing at a boundary which will be Kuhn-Tucker points. Secondly, local maxima are of the form that they are the local maximum of a quadratic form. Okay. The local maximum of okay, I change the variable pi to be z raised to 1 by alpha. Actually, I perhaps shouldn't have used pi here because in fact I use y later. I don't know why I called it pi here. It should be yi equal to z raised to 1 by alpha. I have missed up the notation here probably. So anyway, it doesn't matter. So this is a quadratic form. You maximize it over this set of positive yi satisfying sum of or I of yi raised to 1 by alpha equal to 1. And I will give a figure later soon. So maybe yeah, it's right here. So if you consider the set of yi non-negative or positive, say, so that sum of yi raised to 1 by alpha is less than or equal to 1, then alpha equal to 1 will give this this triangle. As you keep increasing alpha, you kind of alpha equal to 2 will mean there's area under this sort of parabola curve and so on. And alpha equal to infinity corresponds to just these two lines. Okay, there's this unit coordinate vectors. So just keep that picture in mind. So if I define B infinity to be this asymptotic set, then B infinity is this unit vector. B infinity basically amounts to this just unit coordinate, this union of unit coordinate vectors. And I want to define this E star, which is basically the tips of those vectors. So if I go down, it's just these 2 points in three-dimensional case. So B star is just these 2 points. So what I'm going to show is that it goes to the correct element of B star. That's why all this definition. So I define D to be the set where this thing is maximized, and that's where I want to go. And the capital pi sub alpha is the set of pi probability vectors pi which are a local maximum of psi alpha. Okay, so that's this is where one converges for fixed alpha, that we know already. And then the main claim is that if alpha goes to infinity and pi n is in pi sub alpha n, so it's a pi n is the local maximum of for fixed alpha, then pi n will go to B star. Okay, and I'll improve on that later. And that actually and that's not a profound result in the sense that okay, let me not get to that. And if I let alpha also go to infinity and epsilon go to 0 slowly compared to the main iteration, then I claim that this probability vector concentrates on D with probability 1. Okay. So remember, xi itself is a probability vector. So I consider the mass it puts on the local on the global maxima, and that mass goes to 1 with probability 1. That's the claim. So I think I shall make it in good time. The idea of proof is as follows. As I said, the noise added was to avoid unstable equilibria, as opposed to simulated ending, where you also try to avoid stable but undesirable equilibrium. There's a difference. Local maxima here would be a stable equilibrium, but you don't care for local maxima which are not global maxima, so you want to get rid of them. So this is a milder requirement than escaping even the local maxima, although we do go for avoiding local maxima, but we do not do that by means of noise. We do that by tweaking the objective condition. Now, for fixed inverse temperature, I said that if the ODE limit is a nonlinear Kolmogorov forward equation because the transition probability depends on the current distribution. And this is the ODE limit of vertex reinforced random walk introduced by Pimentel and analyzed by Benang. And the equilibria correspond to possible stationary distributions of the vertex reinforced random walk, and they're given by a fixed point equation. So it's just that the fixed point is nonlinear, fixed point of a nonlinear map. There can be more than one fixed point. It's not a contraction. So by broad fixed point theorem, you know that there will be at least one fixed point, but it's a continuous map from a compact set to itself, but you no guarantee that it's unique. Okay, thanks to the connection with replicator dynamics, there's a potential gain with potential minus psi alpha, and then we know that there will be local maxima. The equilibria will be local maxima of psi alpha. Okay. Incidentally, maybe just curiosity item, another little known fact which might be useful. So this, if you look at the replicator dynamics, which sits on the probability simplex, so that ZIT was a probability measure, probability vector. If I change the measure to from ZIT to YIT, say, where YIT is the positive square root of ZIT, then sum of YIT square will be 1. So it sits on the positive quadrant of the sphere. And this for potential gains, replicator dynamics becomes gradient descent on the manifold, namely on a manifold with boundary, namely the positive quadrant of the unit sphere with reflection on the boundary. This is something very useful if you want to do these things. Does not seem to be adequately known. You will find it in, I think it's there in Sandholm's book. So it's very closely related to gradient descent in an indirect way. So now from stochastic approximation theory, we know that there's a asymptotic convergence for fixed alpha. It will go to a sample path dependent local maximum. Now the alpha is changing. Okay. And so it's, the local maximum is kind of a quasi-static for the faster time scale, just as in the 2-time scale. And this is a 2-time scale. But the problem is that the theory of 2-time scale, which I gave, is the vanilla 2-time scale theory, which is mostly what one uses. But here it's not good enough because the fixed alpha ODE does not have a unique limit. Okay, so it has a single limit, but that depends on the sample path. But it's just a bunch of local maxima. There could be one, more than one. So to use the 2-time scale, one has to consider the close convex hull of the stable equilibria, which are all the local minima. You cannot work with a single local maximum. So if we had been working on this problem a few years back, we would have been sunk here. Okay. because one did not know at that time how to handle these things. But by good fortune, this is what I want to say, that there are advantages to grooming good PhD students early in your life. So this paper came up in time for us by Yaji and Bhatnagar with the stochastic approximation of differential inclusions, and that takes care of it. Okay, because we look at the differential inclusion where we replace the basically alpha with the convex of alpha, etc., and then just invoke the results of Yaji and Bhatnagar, and that bails us out of the town. So that's kind of generalized two-time scheme. Now we also need a suitable version of avoidance of traps. So what I mean by that is the fact that the probability 1 you will avoid all unstable equilibria also in presence of adequate noise. So this is what was achieved by that epsilon and noise, and this we prove here. But we adopt some proof which I had earlier for martingale noise, and this becomes a little complicated because this is the two reasons. One was that it is Markov noise, but the worst thing is that it's not on in RD. Okay, it's on a kind of it's in the probability simplex. So that has its own quirks. So we have to handle both of that. Actually, the latter part we were stuck for a while until we realized what to do. And here, this is where I want to give the intuition of what happens. This is interesting stuff, at least for me. So this is a generic picture of an hyperbolic equilibrium. Okay. So this is the equilibrium where these things intersect. So corresponding to stable eigenvalues, you will have these manifolds. Okay. So in linear case, so that they get distorted because this is a kind of structurally stable thing. It gets distorted into some nice surfaces, naively stable manifolds. This is a local picture anyway. Don't forget that. So what happens that if you start your ODE on a stable manifold, you will converge to the equilibrium. So these are unstable manifolds. This other thing where you go away correspond to unstable eigenvalues in the right half plane. So if you are on these manifolds, you will move away. Now, what happens? So the stable and unstable manifolds together form a zero major set in the whole space. Okay, because they are basically union of just low dimensional surfaces, finitely very low dimensional surfaces. So there's a lot of space left. What happens if you start somewhere else? What happens is that if you start near, suppose you start near an unstable manifold, you will go away. If you start near a stable manifold, you will be pulled closer, but eventually you will move away. Okay? And intuition is sort of, I mean, the usual intuition you have in everywhere, like large deviation and so on. Think of this, say, linear system. You will have basically, you will have some kind of weighted sum of exponentials e to the lambda it, I from 1 to n. So for so sum of ci e to the lambda it, so consider some such sum. Okay, and if for all lambda which are negative, or have negative real part, it will go to 0. So eventually, even if the lambda even if the if say lambda 1 is positive, even if C1 is very small but positive, it will end up dominating. The unstable eigenvalues will dominate and eventually will go away. So thing is that for almost all initial condition in the I mean, generically the algorithm will move away. Generically, either in major theoretic sense because these stable manifolds zero major, or even topological sense because their complement is an open dense set. Okay, either way you want, you have it. But then you have to make sure that your noise is rich enough. Suppose your noise is also, when you are on stable manifold, your noise is also along the stable manifold. Then you won't escape it. You you do is you plant some kind of truncated cone at every point here, and you make sure that you get kicked away often enough that you will eventually move away. And that's facilitated by something called conditional Borel-Cantelli lemma, which is a kind of easy consequence of again martingale theory. What it says is that if you have a sequence of events n and you have probability of consider conditional probability of an plus 1 given fn, okay, if that is summable, then n happens only finitely often. So on the finitely often, almost surely, and on the set where it is not summable, it sums up to infinity. N happens infinitely often. So we actually use the latter part. You make sure that the conditional probability sums up to infinity by suitably choosing that epsilon n, and therefore it gets kicked off far enough and infinitely often that you will move away from any unstable equilibrium. So it will go at least to a local maximum, but then you need the annealed landscape to push it further to the global optimum. Now, in the paper, there's more, of course, other than the technicalities. So we actually give an example where we show that from the bandit literature. So actually, we take a cluster kind of graph to the two well-connected clusters with a single link connecting the two. And we show that naive bandit thinking will put you in either not in the best possible equilibrium with probability 1, but we assign some probability with some suboptimal stuff also. But this scheme does take you to the global optimum. Then in the fully connected case, you can say more because the graph questions are gone. You can say a little more about some analytically also. And there's an interesting analogy with ant colony optimization, where what you have is some interesting phenomenon. You don't do any explicit optimization, but there's some the positive reinforcement builds up bias in favor of the optimum, and that reinforces itself so that with high probability, not with probability 1, with high probability you will converge to the global optimum. It will go to probability 1 if the number of ants goes to infinity. Then of course we have numerical experiments. Then this was already I mean, as I said, this is asymptotic result alone. So then the rate of convergence, etc., one can worry about. There are rate of convergence kind of results for 2-time scale for the vanilla 2-time scale algorithms. Not for, I don't know whether fellow bandit students have already done that for the inclusion case. Then those could be plugged in certainly. The regret, of course, that seems very hard. And one thing I would be interested in is some theoretical comparison with simulated annealing, because it does look like accelerated simulated annealing. Instead of tweaking noise, you just move that time scaling which you put on the noise, you move that to the objective function itself. Okay. And this is the last slide. This is my favorite quotation about learning from a well-known British philosopher of the last century. And this is the reference where it appears. It's also there on the archive. Okay, so I guess I have left enough time for questions. Any questions?
Yeah. Thank you, Professor Borkar. We still have about more than 5 minutes for questions.